Autism spectrum disorder, also known as ASD, refers to a set of neurodevelopmental disorders that present with wide-ranging levels of severity, impairments, and characteristics. ASD occurs in all ethnic, racial, and economic groups and affects 1 to 2% of the population. The number of people diagnosed with ASD is growing throughout the Western world, partly due to changes in diagnostic methods and criteria. To put it into perspective, in 2018 there were 205,000 Australians with autism, which is a 25% increase from the 164,000 in 2015. This condition is also associated with a range of costs, including but not limited to medical and healthcare services, therapeutic costs, special education, costs of production loss, accommodation, respite care, and out-of-pocket expenses. In fact, estimated costs are much higher for individuals with ASD or families with children that have ASD. Typical characteristics, traits, and behaviors of ASD include difficulty with communication and interaction with other people, restricted interest and repetitive behaviors, and symptoms that hurt the person's ability to function properly in social areas of life. Current treatment options are directed at symptom management through medication, behavioral programs, and educational programs. Let's now delve into how autism works inside the brain. Specific core regions have been suggested to mediate clinical phenotypes of ASD, such as the frontotemporal lobe, frontoparietal cortex, amygdala, hippocampus, basal ganglia, and anterior cingulate cortex. For instance, abnormalities in these areas may be related to defects in social language processing and attention, whereas issues in these regions may mediate impairments of social behaviors. Inhibitory control deficits and repetitive behaviors are a part of the core features of autism. In fact, its normal functioning requires the synchronization of neuronal networks mostly in the frontal lobe and posterior areas of the brain. Research using various techniques has shown that the connectivity of posterior regions to prefrontal cortex is atypical in people with ASD. Various theories have been proposed in order to explain the pathophysiology and neuroscience underlying ASD. These hypotheses highlight the most important mechanisms in the development of this complex disorder. The most coherent finding is an accelerated total brain volume growth in children with ASD around 2 to 4 years of age. Recent progress has shown that early overgrowth of an ASD brain is caused by an accelerated expansion of the cortical surface area, or grey matter. Thus, accelerated expansion of the brain's grey matter seems to be associated with impaired maturation of the cortical white matter. So what does this mean for the future? Given that the long-term well-being of communities is increasingly determined by the social behavior of individuals, it is now clear that social difficulty is a key source of disability. Although neuroimaging studies have demonstrated both anatomical and functional differences in the social areas of the brain, research on the neural basis of responses to treatment in those with autism is only just emerging. 2 recent studies have investigated the neural response to treatment in ASD. These studies reflect a broader trend to seek objective measures or biomarkers to help evaluate the effects of ASD treatment. In the first study, Dawson et al. Used EEG to measure the brain activity of ASD children aged 4 to 6 years while they viewed images of unfamiliar faces and toys on a screen. The investigators used an EEG-based biomarker known as N170 to indicate a treatment response. N170 reflects the brain's early responses as it recognizes that a face is a face. Both intervention groups showed typical N170 responses following treatment, but those who received ESDM, which is a behavioral therapy for children with autism, had other EEG indicators that were more comparable to the control group children. In the second study, Gordon et al. Measured fMRI changes in 17 children with ASD following intranasal administration of oxytocin. The therapy showed increased activity in these areas of the brain during social judgments and showed decreased activity during non-social judgments. The authors suggested that oxytocin may enhance social functioning in children with ASD. In both studies, the children with ASD process social information more similarly to typical developing children after different therapies, behavioral in the first and oxytocin in the second. This suggests that the extent of neuroplasticity is such that their brains were able to move towards normalizing the processing of social information. These studies both hold a promising future investigation into the underlying neural mechanisms of ASD in response to treatment therapies, which could then facilitate the development of more effective treatments for this multiplex developmental disorder. For disorders of brain development, such as autism spectrum disorder, it is important to fully understand the origins of the problem, as we need this foundational knowledge to truly reach the root causes of these conditions and eventually develop better diagnostic and therapeutic strategies. Therefore, it is important that we strive for the continual evaluation of cortical development and research into the neural mechanisms of ASD to ensure an overall better and well-functioning society for all. Thank you for your time.